A deal's a deal. Nothing is for nothing. Everything has its price. That's by Marguerite Bennett. The atoms of elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. That's by Werner Heisenberg. Those are our quotes of the day, and this is Exus The Podquest.
This show is for seekers. We are seeking answers to the fundamental questions of existence. Questions such as, how did the universe get started? What's the meaning of life? Why is there something rather than nothing? And most importantly, how can we fix the dying problem?
Welcome to Exus The Podquest. Today we're going to be digging into another exciting subject. We're going to be talking about the transactional interpretation of quantum mechanics and what it can tell us about life, the universe, and everything. And we have the absolute best guest possible for that. Her name is Dr. Ruth Kastner. She is the leading proponent of this interpretation of quantum mechanics. Dr. Kastner is a physicist and a philosopher. She got her master's in physics and a PhD in history of philosophy of science at the University of Maryland. She's, again, widely recognized as a leading proponent of this interpretation of quantum mechanics known as the transactional interpretation, or as she might better refer to it, the transactional formulation of quantum theory. She's the author of a number of exciting books, most importantly, The Transactional Interpretation of Quantum Mechanics. The title says it all. Also, she's written Understanding the Unseen Reality, Solving Quantum Riddles, and Adventures in Quantumland. For more on those books and where you can get them, go take a look at her websites. She has two of them, ruthekastner.org and transactionalinterpretation.org. Go over there and take a look. But in the meantime, stay with us as we talk directly with the source. Welcome to Exus The Podquest, Ruth Kastner.
Thank you so much for inviting me. It's nice to be with you.
Absolutely. So let's dig right into it. And as I told you a little bit off air, I'd like this to be a basic review, an idea of an overview of what the subject is, but also, getting into some of the details, but keeping it real like nuts and bolts, if you will. And a lot of the shows like this will start out with, well, tell me about the transactional interpretation of quantum mechanics, but I really want to start more bedrock than that. Can you just tell us briefly, what is quantum mechanics itself for those who might not know?
Yeah, okay. Well, I mean, quantum theory, I kind of call it quantum theory these days, just because I try to get away from that sort of mechanical worldview of Newton. But it's a theory basically about very tiny things that it turned out in the last century, people were having trouble understanding the behavior of very tiny things like atoms and molecules. They basically thought, well, the physics that they had then, which we call classical physics, Newtonian physics, and so on, they assumed that that was basically right, and all they had to do was kind of just fine tune it a little bit. But there were a number of problems that just kind of wouldn't go away. Among these were what's called black body radiation, which is the kind of colors that you get from that come off of things when you heat them up, and you get a certain kind of spectrum or distribution of colors and intensities of colors that came off hot things that just it wasn't working quite right. And then the other issue was these discrete, they could look at these spectra, which were, like the rainbow that you get when you're dividing light up into all its colors. And they found there were these bright lines, these discrete lines that indicated there was something else going on. So there was some phenomena that they ran into that just needed somebody to figure out, wait a minute, where is our classical theory going wrong?
Mm-hmm.
And so at the very beginning of the 20th century, early in the 20th century, people like Heisenberg, Niels Bohr, Albert Einstein, Erwin Schrödinger were really studying this issue. And it was actually Heisenberg who arguably came up with the breakthrough when he basically stopped trying to kind of model things in little mechanical ways, kind of like a tinker toy this is pushing on that. And he just said, okay, this is not working. Let me just step back and look at the experimental data that I'm getting and see if I can just do something with it that makes it fit into basically a mathematical formalism that works to predict what we see. So in certain sense, and there were some guidelines he was using that get into some technical areas, but he basically came up with this kind of mathematical structure that that turned out to work when he started plugging in. You know, I have an atom. I've got this atom that I've put into this excited state, which means it's got extra energy. Then it gives off some light, and I record how much light I'm getting at different wavelengths and so on. I put that in, and then when I put that into my apparatus, it actually helps me predict the things that we're seeing. So, and he actually, at the time, didn't even really know what this mathematical structure was. He wasn't sure what to call it. He called it laundry lists because he was actually writing down like arrays of numbers. Well, it turned out that these arrays of numbers are called matrices, and there is a branch of mathematics that deals with called matrix mechanics. So it turns out that what Heisenberg came up with was a form of what's called matrix mechanics, a way of manipulating these matrices that gives you, that works as a predictive tool. So that's how quantum theory started out. It was not something that someone kind of built and say, okay, I've got my atom. Okay, here's what it's really doing. They still didn't know what the atoms were really doing or what they really looked like. So it was phenomenological in that sense. So that's how quantum theory started out. It was basically a theory that kind of seemed like a patchwork of ideas that seemed to work. And this is why we have so many interpretations, because it doesn't have this clear modeled character, right? So people for a long time were trying to figure out what is going on with this theory. So I mean, kind of in a nutshell, that's what it is. It just started as something that nobody really wanted. They were like, okay, we thought we had it all figured out, but now nature's throwing us some curveballs,
Yeah.
and we're going to have to catch up.
Yeah,
So
it seems to me that that what you've got is a situation where classical stuff wasn't really explaining how atoms and things that are smaller than that were working, and so people were trying to figure out how is that happening, and then and the formalism that you're talking about certainly came about, and now there's all these interpretations of what's happening at that level, the quantum level and below. I'm sorry, the atomic level and below. Can you tell us, give us an idea of what those various interpretations are, and maybe a brief summary of them as we go?
well, okay, so I think the first approach that was kind of an interpretation was when Schrodinger, looked at this matrix mechanics and he said, "Whoa, this is just so abstract. Can we think of this as some kind of a wave?"
Hmm.
And was able to interpret this mathematical structure in some sense as a kind of a wave, because he wanted to get back to a physical picture of some sort. So, in a sense, you can characterize these quantities, quantum states is what we call them. There's states of these objects like atoms and so on. And he was able to put them in the form of something that kind of looks like a wave, and that's called the wave function. So that's arguably kind of the very first interpretation, was Schrodinger saying, look, this is too abstract. Let me look at this and see if I can understand it in some more intuitive way. And if you do it if you look at it from a certain perspective, you can think of these quantum states as having a kind of a wave-like character. So this is where you get things like interference. We've heard of our two-slit experiment, where you're sending, well, with light, we always think of light as a wave. So we'd have send a light beam through two slits and we'd get interference effects. But you would also get that from particles, it turned out. So that's the other thing that was strange about quantum theory, is that everything seemed to have kind of a wave character, but also a particle character, and that's called wave particle duality. So that's another strange feature. Then I guess the school of thought that was centered around Niels Bohr, who was in Copenhagen, was called the Copenhagen interpretation. And I mean, there are lots of, you can get into a lot of heavy debates with people about what is the Copenhagen interpretation. And very likely when I try to describe what it is, you'll get people who say, no, that's not the Copenhagen. So it's a very broad class of approaches, but I would have to say that the fundamental aspect of it is kind of demanding that we acknowledge there's a wholeness to nature, so that this idea of, is it a wave or is it a particle? And Niels Bohr would say, well, it depends on um, the whole experimental arrangement, and we have to look at the entire arrangement to decide, what is the most appropriate way to describe this thing we're talking about, this quantum system. Now, and in a way it was insightful, but it also kind of failed to really get at the essential problem, which was um, turned out to be what's called the measurement problem. And that is where Schrodinger's cat comes in. So that's where we get to, Erwin Schrodinger in terms of getting into the fray here with interpretations. And he was, besides contributing his sort of wave function into sort of wave, he also pointed out that the theory in the form that they had were using it could really not tell you what a measurement was. So that's where we get into a whole bunch of competing interpretations that are trying to explain what counts as a measurement.
Mhm. Okay, so my kind of general understanding of the Copenhagen interpretation is effectively, you've got, it depends on what's happening. If somebody's, if no one's looking at an electron or a subatomic particle, it acts as a wave and spread out, pretty much all over. But if somebody or something interacts with it or views it, looks at it, measures it, I guess you were talking about the measurement issue. If they're looking at it, then it suddenly collapses the wave function, the wave itself, into a localized single classical state. Is that a reasonable statement of it?
Yeah, I mean, you could say that. And of course, this begs that question of, well, what do you mean by looking?
Right.
You
Yeah.
know, and so that's the big giant question mark that
Right.
goes over the Copenhagen interpretation. So it's always begging that question. So when Niels Bohr was saying, well, you have to look at the entire experimental arrangement to decide whether you're dealing with, a wave or a particle. Well, what do you mean by what counts as the entire experimental arrangement? So ultimately, you're always helping yourself in the standard approach to the theory to some ultimate privileged observer person who's looking, and you can't even say what it means to look. So this is where the transactional, I call it a formulation
Hmm.
because it's subtly different. It's a subtly different physics that goes on. And so this is the advantage of the transactional formulation, is it very, very specifically tells you, what do you mean by looking in terms of measurement outcome?
Right.
What,
Yeah.
what counts as the interaction that gives you that, what you said, that discrete, clear outcome? Okay, so in other words, like if you're doing the two-slit experiment with electrons who are propagating in this kind of wave-like way, um, you can send them through one at a time, and they're still going to exhibit this interference, but you're going to get ping, you're going to get a little electron spot there, you get an electron spot there, right? So you're going to look at your photographic plate, and you're going to get that particle-like registration, but collectively it shows you this wave-like thing. So what's the problem with the conventional theory is it can't tell you why you ever got that particle-like behavior. So
Yeah.
that's where the actual interpretation comes in with a specific explanation.
Yeah, it's so fascinating because the general person out here, when you're looking at things, we say, okay, well, there's a subatomic particle, and science is telling us that that is in a very like we in a state of existence that we can't really put our intellectual arms around. It's fuzzy, it's indeterminate, completely subject to being all over the place, and maybe in all these various superposition of all these possible states, and then suddenly something happens and then it becomes a classical one single thing that we can all identify as an electron or a photon or something along those lines. And the Copenhagen interpretation has this concept, and it has this problem with the observer effect. I take, and of course, there's other interpretations. The many worlds interpretation of quantum mechanics, or quantum theory, as you say, very good, and David Bohm and pilot waves and stuff like that. But let's join the transactional interpretation. What does the transactional interpretation say about what's going on with making these things that are in this indeterminate state into something that's classical and understandable?
Right. So here's where we get into what's missing in the conventional theory. This gets a little technical, but this wave-like behavior where these quantum systems really have indeterminate, properties, in the sense that it's really, I'm sorry, you really can't say that that electron is in one place or the other while it's propagating through these slits, right? You really can't. Sorry, folks, that's just the way electrons are. So there's a portion of the theory that describes that behavior. And the problem with the conventional theory is that that's the only kind of behavior that it can describe. And so the technical term for that is unitary evolution. So that's just our fancy term, impress your friends at your next cocktail party with
There you go.
unitary evolution. And what that is Schrodinger's little wave function propagating along in a very specific deterministic way. So you've got what's being described as a wave. It's non-local. Okay. Well, that's very useful and it's really accurate at a certain level. But what happens is that there is also a different kind of physical behavior that goes on when you're working with the transactional picture, and that's called non-unitary.
Mhm.
And what it does is it means that this deterministic evolution is actually interrupted in a very specific way, and that involves our screen. Okay, so we've got our photographic plate. So what we've got in the transactional formulation, what we do is we point to the need to take into account, say, a laser or some light source. Okay, so we've got a light source. And in the conventional theory, that's all that we care about. Oh, there's a light source, it's popping out photons or whatever, so let's say it's photons that we're dealing with, just because that's simpler to deal with. Okay, but actually, at a very micro level, um, there is a slightly different way of understanding the way the electromagnetic field behaves. And the electromagnetic field is where we get photons, where we get the particles of light. So the electromagnetic field is basically all of these kinds of energies that are related to light. We've got radio waves, infrared, gamma rays. So there's a whole spectrum there. But we're working with visible light. So we're working with what's called a quantum of the electromagnetic field. Well, it turns out in this alternative way of understanding field behavior, the story doesn't the story is missing, the usual story is missing the absorber. So in the transactional account of the electromagnetic field behavior, absorbers are active. So we've got, say, atoms hanging out in the screen photographic plate. They are available to this emitter, that we usually think of just tossing out photons autonomously. In the transactional picture, that's not what happens. You basically have a kind of a mutual interaction that goes on between the uh, the emitter and the absorbers. And the absorbers have to do something in order for you to get a real photon that goes from your source to one of those absorbers. So they have to actively respond. And when you look at the mathematics of that, what you get is this so-called non-unitary interaction that tells you that's a measurement. So what you get when you get a measurement, what defines a measurement, is that the things that could take up energy are doing something. They are actually responding in a subtle way to the emitter. And that the emitter, the person who first came up with this picture in terms of the quantum theory application was John Kramer from the University of Washington. And his terms for these behaviors were the offer wave that comes from your laser or something, but you also have a confirmation wave that's coming from all these different absorbers in the screen. So they're responding and they're kind of like entering the lottery, you know? So what you've got is this general offer wave that's coming from your source, and it has all these offers coming to it. And the nature of those offers has to do with, you know, what's in between and the whole configuration. So this is where we get the kind of the Niels Bohr insight, you know, that's valid, that the kinds of responses or confirmations you're going to get from your absorbers are going to reflect, you know, what the whole configuration is. So you get these responses, and that's what counts as a measurement. But then you do have a collapse, because obviously they can't all, if you have one object coming through, if the field has one photon, it can't go to all of them. This is the non-classical part. So in the classical theory, energy can just spread out like that, right? But the quantum theory means it's comes in little hunks. So if I've only got one hunk, one of these is going to have to win. And the probability that it wins is given by this quantum probability rule, the so-called Born rule. So that's kind of in a nutshell that's measurement. And it involves what's called absorber response.
So if you have an emitter, let's say it's the laser, and it shoots out, let's say, one photon, and it goes forward, and it hits, and it's going to be hitting a plate in the back, in the background, and the absorber field here, this plate, sends out has a bunch of absorbers, and one of them is going to get selected, right? Or one of them selects, and that there's an interaction, and that becomes a measurement. If that's the case, what happens when that happens? So let's say you had the absorber, the winning absorber over on the plate gets the interaction because it's now connected with the offer wave. You've got the offer and acceptance. There's a transaction. What then results? Because you have a photon going out is being the offer wave. What happens then? What happens?
So what you have, the offer wave is not an actual photon.
Oh, okay. Okay.
Yeah? So the offer wave is that Schrodinger spread out thing, the Schrodinger wave. That's the offer wave is that usual wave-like thing that's behaving wave-like way, picking up interference. The conformations are all of those eligible absorbers are responding to the component of the offer wave that they receive. They're not going to get the whole thing. And there's going to be interference. There are going to be some of them aren't going to get any offer wave at all because they're in the dark part of this interference pattern, right? So you're still going to get those interference effects, and each of the absorbers is going to respond again in a wave-like way. So they really are wave-like in that sense, that they are responding in a way that is going to retain the interference, and that's going to dictate the probability that when you get this collapse, you are going to get a photon that will end up going from the source through both slits. Sorry, photon, it's still going to go through both slits, right? Because it's part of this interference. But once you get that, you basically, this sort of non-unitary process kind of has two stages, just to get a little more clear. The initial stage is this offer confirmation interaction. This sets up kind of this lottery where it means that a measurement is happening, but it's not telling you who won the photon yet. But there's a measurement situation is happening. Okay, now let's announce the winner. We open the envelope. We have a winner. Okay, it's this absorber here on this little pixel. Okay, so what happens is the photon ends up being a two-slit photon. It went from the source, in a sense, through both slits, and it ended up at that absorber. And meanwhile, this also helps you with these so-called null measurements, because all of those pixels that didn't get the photon, they still participated in the measurement interaction. They lost, but it's sort of like when you enter a lottery, a bunch of people enter the lottery, and that's what a lottery is.
Mhm.
Only one person can win, right? So that's kind of what it's like. It has those two stages to it.
Yeah, it's fascinating. In terms of the winning absorber, is there something that dictates what is going, who's going to be that winner? Like in a lottery, if everyone's pretty much the same. You're lucky if you won, like wildly lucky, but there's nothing that makes it weighted in your favor. But in this situation, is there something that makes it more weighted in favor of one outcome or one absorber, I should say?
Yes, I mean, the different absorbers will have different weights in general. Now that you can have an experiment where you could have different absorbers who would end up being like, say, three absorbers that would all have 1/3 probability. So you could certainly have a situation where they would have the same probabilities. But in general, they are going to be weighted, and they're weighted by this thing called the Born rule,
Mm.
the quantum probability rule. And this interaction of the offer and the confirmation responses mathematically gives you that rule. So that's the other nice thing about the transactional approach, is that when you look at the mathematical description of it, this so-called Born rule falls right out. And it's basically just the product of to get a little technical, the amplitude of the offer wave component that went to a particular absorber times the amplitude of that response, and you square there, so it gets squared, and you get this probability.
Okay, so
So, but it is fundamentally indeterministic. So again, there's only probabilities,
mhm.
right? They're weighted, but there's still nothing that's going to say in any particular run that one's going to win, right? So
Okay.
it's really deterministic in that way.
All right. And so once there is a winner, okay, you've got this, the weighted, it's somewhat weighted in favor of the highest probability. And then you get,
Mhm.
effectively the offer and the confirmation have now resulted in a transaction, and you have a photon, right? That's effectively right. All right. All right, but you now only have one photon in existence as of that transaction. That's not enough for, let's say, there to be light in this room that we're in. How is it that you get stacked up all these various numbers of photons so that you get light in a classical form?
Well, I mean, you have a lot of very frequent transactions. So, I mean, when you're dealing with something like a photographic plate, these macroscopic objects, we've got zillions of atoms in there. We've got
Okay.
zillions of absorbers. So, and usually, and I don't pretend to know, like the technical details of exactly how these photographic plates work,
Mhm.
but they are basically, made of excitable atoms or molecules, so that what's happening is they're absorbing, they're participating, say, in a transaction, and then pretty quickly they're going to radiate again. They're going to become emitters, and they're going to dump that excess energy to some other absorber in the environment. So they become available again. So that's really what the macroscopic world is. It's just huge numbers of transactions, so frequent that it just looks like, you're not going to see this very discrete kind of behavior unless you really look hard for it.
Yeah.
You have to really, yeah, be
That's such a
careful.
such a very very interesting concept. That's why when I was reading and studying about this, I'm thinking that's just like the really cool part of it is that you've got this almost it seems like there's well, let me just ask the question: is there some type of guiding, or it's not guiding but organizing principle behind it so that everything doesn't just become a blob of light, but rather coherent classical light, or and I like to use this example. Here's this ball. Okay, I bounce this ball everywhere I go. All right, but in order to make this ball, I mean, you're talking about trillions and trillions and trillions of transactions under this formulation. Is there something that is organizing the process so that we get a ball instead of just a blob of nothingness or a mixture of stuff?
Well, I mean, there's sort of different aspects to your question.
Yeah.
You can look at a kind of the so-called classical limit of when things are going to look more like classical light rays and like flashlight beams and so on. And that has to do with the wavelength of the light being very, very tiny compared to the dimensions of the things it's going to have to interact with when it being in this wave-like description. So if in that respect, the way you can kind of recover what we call the classical limited, which is called ray optics, as opposed to like wave optics, is by just having the wavelength of your light be very, very small compared to the dimensions of your like the slits that you're going through, so that the wave nature of the light is like barely noticing the slits as a kind of impediment, if you will.
Mm-hmm.
Once the dimensions of the experiment start to get to the order of magnitude of the length of it, that's when you get this diffraction and you get more of this obvious wave kind of interference quality. But I mean, in terms of the macroscopic objects and so on, yeah, you can. I mean, that's kind of where intention comes in, really, because like, if you want to make a ball, that you're going to use your own volition, and you're going to just take materials and make a ball out of it, right?
Right.
So that's where, in a sense, where volition comes in, that we shape the objects around us.
But yeah,
We,
at the subatomic level, though, you're not saying that there's like an organizing principle that puts all the various transactions together in order to make a classical object. It's just something that's indeterminate and it happens.
that's us, really. I mean, that's kind of, that goes to this question of, how is it that these very structured and almost designed and organized objects can come about in against the backdrop of the second law of thermodynamics, which tells you that, in a sense, that disorder always increases, right? So that's kind of a different question, but no, the transactional interpretation is not going to give you trees, it's not going to give you a picnic table,
Okay.
it's just kind of telling you how the electromagnetic field really behaves, and what kind of interactions are going on that give you determinate things. They give you those particle-like localized things,
Hmm.
so that everything isn't just all spread out. And that's because things are undergoing transactions all the time. And
Yeah.
this localized things. So it's not like someone has to look, this phrase, the observer effect, is just, again, question begging around the notion of what counts as a measurement outcome. What is it that I'm doing in the world that gives me a measurement outcome? And pointing to observer as a placeholder for that question mark, right? Because, well does it, back to the Schrodinger's cat experiment, that does the cat count as your observer effect? Okay, well then why isn't he collapsing? And so they can never say what that effect really is. And that's why you need this mechanics, I hate to use the word, but this physics of what is the field really doing?
Yeah.
And the key is that it's a mutual responsive kind of behavior that's giving us that measurement outcome.
And is it fair to say that if the transactional formulation is correct, there's really no need to come up with and to rely on the many worlds interpretation where there's splitting off of all these universes every time there's an event? Is that fair to say?
That's fair to say. And in fact, the many worlds approach comes from not being able to say what counts as a measurement, and so a measurement, and gives you an outcome, and just basically denying that a unique outcome ever happens. But it doesn't really work, because they still can't say what counts as splitting. So then they kind of just push, you kind of got a lump in the carpet, and you push the lump until it goes under the piano bench. Here, I got a piano here. And you don't ask, but if you look under the piano bench, hey, isn't there a lump under the bench here? And that's what that is, because if you look at the technical aspects of the Everettian approach, I mean, I admire Hugh Everett's effort. I think his heart was in the right place. He was trying to deal with this problem, but But then he missed, I think, the crucial thing that you really do have a physical interaction that counts as a measurement. And if you don't have that, then you may try to retreat to the idea of worlds and splitting, but you still can't define, when am I going to split? What is it that splits and why? And the failure to do that ends you up with specific inconsistencies. So you can show that different observers would disagree on where the split happened.
Yeah.
And they would end up making different predictions that are consequentially wrong, or disagree with each other.
Yeah, as I was looking into the transitional formulation, it did occur to me that this is a much simpler, more elegant, if you want to say it, more simpler, better approach than the many worlds approach, which requires this splitting off. And then there's, like you said, there's all these questions about it. Whereas if you accept that there's a transaction that occurs and that is the event, that is the measurement, if you will, then you don't need an infinite number of worlds in order to account for what's happening here, which I think was really, really cool.
Well, thank you. Yeah, and I think the key, the key leap, if you will, is allowing for possibility. Is allowing that, there can be possibilities that are real, that are being described by the physics, but not all possibilities can happen. It can't all be actualized. So that's what's going on in this picture. And if we don't have that, and if we don't have that physics that describes that process of how possibilities get transformed into actualities, then we end up with this attempt to kind of make everything actual. So there's I think that this goes to kind of, maybe esoteric philosophical considerations, but this kind of approach is called actualist. So it's kind of a philosophical, metaphysical predisposition that most of us have, just because we're in the classical world, and that's what we've been taught. That stuff has to kind of exist in what I think of as an actual local space-time manner, or it doesn't exist at all. And it's that either or thinking that puts us in that dilemma that leads to things like the Everettian interpretation, where, okay, I can't explain how one of these, has something and happens. So I'm just going to say everything happens.
Right.
Doesn't quite, it doesn't quite work.
Yeah, it does. It does seem to just basically default and say, well, we'll just include everything, and you can explain it away that way. Kind of like you throw the word infinity around all the time, and it's like, well, I don't know if that. I think it should be more carefully used. But anyway, I know, as always on the show, time is just evaporated, and I know we're up against a clock. This is a fantastic introduction to this really exciting idea, the transactional formulation, and I'm going to use that, the transactional formulation of quantum theory, and so I'm going to urge all the people watching to go out and check out several things. First off, your books. The Transactional Interpretation of Quantum Mechanics is probably the one you want to focus on right away. But the other ones that are out there, the Understanding the Unseen Reality and Adventures in Quantumland. Everyone, go out and get these books. Go to the website, ruthekastner.org and transactionalinterpretation.org to get an even deeper understanding of what we're talking about. Hopefully this has whetted your appetite to go out and find out more about this really, really cool idea in quantum theory. Also, give us your comments. Let us know what you think about this. Go over to exusthepodquest.com. Let us know what you think. Give us your comments there, obviously. But also go in on YouTube. Give us your comments in the comment section, which is wide open as always. Click like on this episode. Even if you don't like it, you will. But click like even if you don't, and keep doing it over and over again. You know the drill. Also, subscribe to the show because the more subscribers, the better, and the algorithm gets fed, and everybody's happy. Get your 10 people who don't already subscribe to the show. Go out and drag them in off the street. Make them be subscribers to the show. So again, the show builds up. Dr. Kastner, I cannot thank you enough for being on the show. This was a fantastic overview of your thrilling theory here, and again, I thank you very much for joining us.
Oh, it's my pleasure, Brian. Thank you so much for inviting me.
Oh, no problem at all. Again, to the audience, you guys do all the things we just mentioned, do all the fun stuff, and then we, of course, will be going ever forward.